So what does it mean to be an ideal gas? An ideal gas should stay gas at all pressures and temperatures. And I mentioned that steam. Is steam a very ideal gas? No. And so I have this empty can here. It's not empty. You know what I have inside this can? I put some water inside here. You hear that? Water. Maybe it's too much water. I put a little bit of water in here, like this much. The reason I put some water in here is I'm going to heat it up and generate this. So I'm going to fill this can up with steam. The steam should purge the air out of here, or a lot of the air out of here. So let me go ahead and heat this up to boiling. So I'll try to put the bottom of the can right at the tip of the cone here. Bring my safety goggles though to risk it. I put too much water in here. Well, one of the things about water takes some time to heat up. It takes time to heat up because it has something called a high heat capacity. Do you hear it? All right, it's boiling now. And what I want to do is I want to purge as much air out of here as possible and get this thing filled with steam. And so now I have this, this can is going to be filled with steam. And what I'm going to do is I'm going to, you see this beaker of water? I'm going to invert it and then seal it. I'm going to use the water to seal the top of this and then cool it down. Cool it down a little bit. So I want to get it to a good boil. I might have put too much water in there. Okay, and then maybe you've seen this before, but let's go ahead and do that. So that's it. And so what happens is, you know, the steam goes from a gas, and then when it cools down, it condenses into a liquid. What happens to the volume? Well, the gas volume is big, but the liquid volume is very small, and so it creates a vacuum. So see here is just the vacuum. And then air comes in, and well, the weight of the atmosphere will come in and it's crush the can. So that's the demo here. Right. As far as another useful equation to know, and this one's derived from the ideal gas law as well. It's called the molar volume. So this talks about the derivation. I'm not going to derive it the same way they derive it. The molar volume is pretty useful. We don't even really need this, you know. The molar volume is, you know, how many liters does 1 mole of gas occupy? Well, it depends on the temperature and the pressure, obviously. And so the molar volume, MV, is equal to how many liters, that is volume, does a mole of gas occupy? So volume per mole, that's what we're, V over N. And so this is what we're going to do with this. What we're going to do is we're going to look at N here. If we look at N is equal to PV over RT. Just rearrange the ideal gas law. So N equals that, and then we'll just plug it back in here. So what we get here is that we'll have V divided by PV over RT. Well, the volumes will cancel out, and then what we're going to do is we're going to invert and multiply. So it's just going to equal RT over P. So if we want to figure out how many liters a mole of gas occupies, then all we need is the temperature and the pressure, and then we can figure it out. So molar volume is equal to RT over P. That's a relationship that they showed down there. And so there's something called standard temperature and pressure, STP. The common reference condition of standard temperature is 0 degrees C. That's standard temperature. Standard pressure is 1 bar or 1 atmosphere, depends. What you do. It's 22.7. When I was taking intro chem, I had to memorize it. I had to memorize the molar volume of gas at STP, standard temperature and pressure. But did I tell you? I memorized it. I still have it memorized. How many times have I used it since intro chem? 0. What a waste. What a waste of memory, because my memory is marginal and I can't it's one of those things I can't forget because I work so hard at memorizing it. I wish I could forget it and then remember more important things, but I can't. So, you know why it's so useless? It's because who works at 0 degrees C? Is your lab set up at 0 degrees C? No, you'd have to work with a thick coat on. I mean, it's not that you can't work at 0 degrees C in the lab, but who does? Nobody. And so this is why I never found it very useful. You'll find the only use that you might see for it is making comparisons. What's the molar volume of this gas versus that gas, But it's not. So why bother with this equation? Why bother with this equation? Is there 2 useful molar volumes to know? So STP is not so useful. STP, the temperature is 0 degrees C, the pressure is 1 atmosphere or 1 bar, depending on where you're at. In Canada, it'd be 1 bar. In the U.S., it's probably 1 atmosphere. But not useful. Not useful, therefore, I'm not going to spend any time. Okay, what's more useful? What's more useful is room temperature and room pressure. And so what is room temperature and room pressure? So what I found much more useful is the molar volume at room temperature. Room temperature is 298 Kelvin or 25 degrees C. And room pressure. Room pressure is going to be 1 atmosphere or 1 bar. And so let's see how much the gas occupies at. Okay. So the example we're going to do is we're going to do at 298 Kelvin and 1 atmosphere. What is the molar volume? And so if I do this at 298 Kelvin and 1 atmosphere, then the molar volume is equal to RT over P. R is 0.08206 meters times atmosphere per mole Kelvin. T is 298 Kelvin. P is 1 atmosphere. We'll just say exactly 1 atmosphere. So we look at the units here, and the atmospheres cancel, the kelvins cancel, and that leaves us with liters per mole. So let's see what it is. So 0.08206 times 298 divided by 1. I'm not going to do divided by 1 part. And so it comes out to how many sig figs am I allowed? It's like 3 sig figs. 3 sig figs here. I'll call 1 atmosphere exact. So we're going to get 25 or about 24 and a half liters. 24 and a half liters. So 1 mole of gas at room temperature and room pressure occupies 24 and a half liters. Okay. Now, if I cool it down, what's going to happen? As I cool it down, will the gas shrink or expand? It shrinks. So if I go from room temperature, which is 24, I mean, it would be a room temperature, which is 298 Kelvin, 25 degrees C, and cool it down to 0 degrees C, 273 Kelvin, then the volume shrinks. It goes from 24 and a half liters to 22.7 liters. See that? So this is a useful number to know, 24 and a half liters. Okay, the other scenario is if we're dealing with bars, like in Europe or Canada, they'd be dealing with bars. And so let's go with 298 Kelvin and 1 bar. What is the molar volume? Now, what's the relationship between bars and atmospheres? Well, it turns out that 1 atmosphere is equal to 1.01325 bar. And so an atmosphere and a bar are about the same. If you look at 1 atmosphere, it's about 101 bars. So they're very close. And so if you're listening to the weather, a bar is very similar to an atmosphere. And a millibar is kind of like a millimeter of mercury. Not quite. And so millibars. Well, anyway, let's look at this. Which one's bigger, an atmosphere or a bar? Well, it looks like a bar is bigger, but a bar is actually smaller because you need more bars to make 1 atmosphere. And so we need a little bit more than 1 bar to make 1 atmosphere. So bars got to be a little bit smaller. And so if we're looking at a bar, what happens at lower pressures? Does the volume expand or does the volume contract at lower pressure? So if we decrease the pressure, will the gas expand or the gas contract? It should expand. And so the molar volume should be a little bit bigger than 24 and a half liters because at 1 bar, the pressure is a little less than 1 atmosphere. 1 atmosphere is more pressure, 1 bar is less pressure. So can you calculate it? What is the molar volume of a gas at room temperature and 1 bar?